Hi there, and welcome back to another video on conditional probability. This is chapter 2, as you can see, for the year 13 portion of the 2-year Edexcel A-level maths course. So the first bit of chapter 2 was just recapping Venn diagrams, really. We didn't do anything, to be fair, on conditional probability. So this is the first part of the chapter where we explore the idea of conditional probability properly, and we use two-way tables here to help us see what's going on and how to categorize the different areas correctly. So let's get started with a selection of warm-up questions. So the first two relate to this chapter. Questions 3 and 4 go back to year 12 hypothesis testing, which is always worth revising. So I suggest you pause the video here, have a look at the questions, try them on your own, and then press play when you've attempted them to the best of your ability, so you can then see how well you've done when I taught you through them. Okay, so let's get started then with warm-up question 1. So question 1, we have a two-way table showing the number of students studying art and biology at some sixth form, either sixth form college or a sixth form at a school. We don't know. So we need to use this table, interpret it properly, and write down the following probabilities from it. First of all, the probability of it being A. So in plain English, this means what's the probability of a student studying art? Well, the students studying art are these lot. So studying art, we've got 34, but we don't know out of how many we have yet. So what we need to do is to total up all these values. So the grand total number of students, we just need to sum these four values in the table. So first of all, I'm going to add up the number doing art. So we've got 10 plus 24, 34 art students, and then we've got 12 plus 4 students that don't do art. Students are either going to do art or not do art, so by adding up these four numbers, when you think about it logically, we have therefore necessarily got every single student. So that's got to be the correct total. So that's 50. So 34 out of 50 study art. Therefore, the probability of randomly selecting a student that studies art would be 34 out of 50. The next one, the probability of studying biology. Well, studying biology is going to be this row here. There's 10 students that study biology and art, and there's 12 students that study biology but do not study art, making a total of 22. So that's 22 out of 50 students for part B. Finally, for part C, this means the probability of selecting a student that studies art and biology. This is the intersection of where we have A and B together. So on this table, it's just where the art column meets the biology row, which is this one here, which is the 10 students that do both art and biology. So the probability of selecting one of those students is 10 of them out of a total of the 50 students selected. Of course, you can simplify these fractions if you want to, but with probability, even at A level, there's no force for you to actually simplify down fractions if you don't want. If you do, that's fine. If you don't, equally good. Question 2, a Venn diagram 1. So we've got here, again, linked to question 1, the number of students studying art and biology at a sixth form. So it's partially completed. And for part A, we need to use a two-way table from question 1 to complete this Venn diagram here. So let's get started by reminding ourselves of the table we had from question 1. So there it was. So first off, art and biology. So this one here, like 1 part C, that's for students that study both art and biology. This is where A and B intersect, so that represents this region in the Venn diagram in the middle. The next one, this one is biologists that don't study art. So there's 12 students that only do biology but don't do art. So these students will just be the ones in the B circle only, the ones that aren't touching this A portion of the B circle. So just this major crescent of circle B. So that's for 12. The next number, this 24, is for the students that study art but not biology. And as is labelled, that's this region there. And so the final region, which hasn't been labelled yet, is the outside. That's the students that neither do art nor biology, which makes sense because in the table it's that they don't do art and don't do biology, and that's 4. So the outside region is represented by 4 individuals. So we've done part A, that's the Venn diagram done. We can now use this to think about the probability of selecting a student randomly that is not an artist and also not a biologist. So let's think first of all about what A dashed means. I've just said really means anyone not studying art. So I'm going to highlight using red lines all the regions apart from region A. So these red vertical lines represent the region A dashed. The region B dashed, in pretty much the same way, is everything apart from circle B. So I'm going to colour in everything apart from circle B, this time though with horizontal blue lines like so. Now we want the intersection. We want where we've got red lines and blue lines together. So we're wanting where it crisscrosses over, where it's like a tartan sort of kilt or something like this. So where you can see the lines crossing over, well there it's just blue, there's just red, and in the middle's nothing. The only part they're crossing over is the outside region, which links to this 4. In the same way, A dashed and B dashed we could have got from the table by considering this here. Where the not artists column crosses over with the students that don't do biology, this row here, they intersect at the number 4 like you can see. So either using the table or the Venn diagram, you should come to the same conclusion when you get skilled enough and used enough to using Venn diagrams and two-way tables. Just by seeing where the not biology row intersects with the not art row. So if you just see where they meet, the non-biologists meet the not artists here, that's the intersection, this cell 4. So sometimes using a two-way table is just as easy, if not easier, than using a Venn diagram. So you can use both approaches to work out conditional probability questions. So this is why we're introducing today two-way tables. Well, not introducing two-way tables, you've probably seen them for GCSE, but what I mean, of course, is introducing two-way tables in the context of how to do conditional probability questions. Anyhow, I'll stop muttering. The probability, therefore, of A dashed joined up with B dashed is these 4 people here, out of a grand total of 50 students altogether. Question 3. We're talking about a single observation, X, is to be taken from a binomial distribution B 28, P. So 28 trials and P is a proportion of how many successes we actually see. So this observation is going to be used to test the null hypothesis, where the proportion is 0.37, against the alternative hypothesis, H1, where the proportion is going to be greater than 0.37. First of all, we have to use our calculators to find the critical region for this test, use a 5% significance level, and show your method clearly. Well, my suggestion is, to be fair, always to just sketch this out on a diagram. So binomial distribution is a curve. So there's 28 trials, so we can have as few as 0 out of 28, somewhere in the middle, and down here 28 out of 28. So this is the distribution of the random variable x, where big X follows a binomial distribution 28 and P. So what I'd always think about as well, generally, is how many would you expect out of 28 to be successful? So if 37% is what you'd expect, your expected number would be 28 times 37%. Or 37% of 28. So let's work that out. So 0.37 multiplied by 28 is about 10.36. So the mean expected is somewhere about 10.36. So the critical region here is at the higher tail, because we're saying this proportion for H1 is greater than 0.37. If we times 28 by a high proportion, that gives us a greater value. So we're looking at the higher tail only, where it's greater than this value. So the higher tail is this proportion here, and because we're using a 5% significance level, we need to find the first critical value, this here, which makes this region fall to a proportion of 5% or less of the curve. So this area here of the curve in red needs to be no more than 5% of the curve. So what's the first value that achieves that area to be this value or under? And to be honest, with a good enough calculator like the Casio ClassWiz, you can guess your way to success very, very quickly indeed. So the sketch lets you see that we're going to be looking at the higher tail. So that's 10. The maximum at this end is going to be 28 because there's 28 trials. So just randomly pick some number in between 10 and 28. So my initial guess, and I promise you this was a guess when I was doing it, I just tried for 15. So is it 15? So what's the probability of x being 15 or greater? That's going to be 1, subtract the probability of x being 14 or under. So we're wanting the first value that makes this fall to 0.05 or under. So this value here, we're wanting to see on our calculator to be just a shade over 0.95. £1 take away 95p or more will get us to 5p or less. So you can get a feel for if the value's close, for if the calculator gives you a value for the calculation which is 0.95 or at least close to it. So on the ClassWiz, what we can do is get into the right mode. So the way we do this is we press the menu screen and we scroll using these keys to option 7 and press equals. We now want the binomial cumulative function, which we don't see here, so we need to scroll down. It's now option 1, so press 1. You want the variable function, so press 2. And my guess here is to compute the probability of seeing 15 or higher. So obviously, though, to do that, we do 1 minus p, 14 or less. So we input 14 out of a total of 28 it was, and the proportion was 0.37 by h, 0. Now that gives us 0.945, so that's a shade under 0.95. So this won't be critical yet, but let's write it down, because our working makes it clear to the examiner that we deserve our marks. So that's 1 minus 0.94, what was it now, 0.9454 and so on. So go back to normal mode, so press menu 1 and do 1 minus our answer, it'll be stored for us. That's 0.0546, which we can see is still greater than this 0.05. So that's not critical yet. That's me being very lazy. I probably should have just wrote not critical. Ironically, me having to explain my laziness is actually taken longer than me just writing not critical in the first place. So there's a accidental lesson in itself, not to be lazy, everybody. Right, so the next one. Because this isn't critical yet, we go 1 higher. So we can sense, or should be able to sense with practice, that 16 is going to be the critical value. But show this working to the examiner as evidence that you know what you're doing. So probability of the observed value being 16 or greater, same idea, 1 minus p, x being 15 or under. So 1 minus, and then this time it's going to be, go back to menu 7, CD variable. This time I was trying 15 out of 28 with our p-value of 0.37. Press equals and equals again. Now you can clearly see when we do 1 minus this, we will be under 0.05. And because that's the next one up from what we tried before, which was not critical, this therefore has been proven 16 to be the first value that sends us into the critical region. Therefore x equals 16 is our critical value. But let's finish it off to formalise it and to secure our marks. So it's 1 minus 0.976-ish. And if we go back to normal mode, 1 minus that, you see it's about 2.3%, 0.0238. And that is now under 0.05. So therefore, we can say critical value. I know it's not asking us for the critical value, but it can't hurt for me to remind you what the critical value is. It's the first value that would cause you to fall into the critical region from the bit which is not critical. So from going from non-critical to critical is that first value you cross the threshold for. So we've just shown that x being 16 or greater sends you into the critical region. So your first critical value was x equaling 16. And the critical region, which is what it's actually asking us for, is the proportion of the graph in terms of our variable x, which would cause us to reject h0. So it's everything from our critical value, which was 16 and higher. So the critical region is x greater than 16 or equal to 16, or we could write it like this, all the way up to 28, because 28 is a maximum it could be at any rate. Finally, question 4, which links to question 3, the actual value of x observed was 17. So state a conclusion that can be drawn based on this value, giving a reason for your answer. Well, 17, if 16 is here, 17 would be just next door to the right of it, but definitely in the critical region. So because it's in the critical region, that means we have evidence at this 5% significance level at least to reject h0. So what we need to say is something like this. Something like there's evidence to reject h0 at the 5% level of significance. This is because, this is your reasoning, this is because 17 is in the critical region. So now I hope we're all warmed up. Let's have a look at the new topic proper, conditional probabilities. So what do we mean by conditional probability? Well, conditional probability, it's the probability of an event. It can change depending on the outcome of a previous event. So an obvious example could be the probability of you being late for your lessons. That might change depending on whether you oversleep or not. If you overslept, chances are you might be late for registration or period 1. And similarly, if you follow sports, the probability of a football team winning a match that's already started depends on the number of goals already scored. If a team is 2-0 up 80 minutes into a game, they're much more likely to have won than if they were 0-0 80 minutes into a game, because it's conditional on those 2 goals they scored. It's obvious really when you think about it in that way. So next, situations like this, we can model them using conditional probability structures. So with maths, we have a vertical line to denote we're talking about conditional probabilities. So the best way of me explaining this is just showing you what it looks like and then explaining in context. So if we had the probability of B and an event A, the probability that event B occurs, given that A has already occurred, is written as P, then in brackets B slash A. So this slash needs to be read as given that this thing here has already happened. So what's the chance of B happening? Now I'm telling you that A's already happened. So this is like the extra information that you need to almost read first in order to answer this bit. Probability of B is conditional, it's dependent on this bit here. In pretty much the same way, the probability that B occurs given that A has not occurred is P for probability, then brackets, B occurring, vertical line for given that A dashed has occurred. A dashed means not A. So if A dashed occurs, that's the same as saying A has not occurred. Whatever comes after this vertical line is what we're telling you is already the case. Based on that being the case, now we're giving you extra information. How does that affect the outcome of B? If, of course, 2 events A and B are independent, then if A occurs, or doesn't occur for that matter, that would have no bearing or influence on the probability of if B will occur or not. And the other way around. If B occurs or doesn't occur, that shouldn't affect if A occurs or not. One doesn't affect the other because they're independent. They're free from each other's influence. So because of that, we can use this conditional probability to help us. So for independent events, A and B, the chance that A happens, given that B's happened, won't matter. That's the same as the probability of A happening if B doesn't happen. It's just a probability of A generally speaking, because whether B happens or doesn't happen, A doesn't care. A happening or not is completely independent-minded of B. And similarly, same for B in place of A. This bit here is just B switched with A. So like we said here, vice versa. And this condition here, if two events A and B meet this criteria, that is sufficient to determine if those two events are independent. So if this can be shown to be the case, probability of A given B is the same as the probability of A given not B, which is the same as probability of A. This proves two events are independent. You can also sometimes solve some problems involving conditional probability by considering a restricted sample space of the outcomes where one event has already occurred. And we're going to have a look at restricted sample spaces soon, particularly in the context of two-way tables and other tabulations of sample spaces. First of all, worked example about a pack of playing cards. Maybe I'm just a traditionalist, maybe I'm just sad, I don't know, maybe both. But although packs of cards are going out of fashion for probability questions now, I do like to just remind you of what cards are, just for history if nothing else, I don't know. So you've got 52 cards in the deck. They're here, 52 of them. So let the heart symbol represent all the cards that are hearts. There's 13 hearts from ace to king. The diamond symbol represents the diamonds. There's 13 diamonds. This one is clubs. There's 13 clubs at the top. And this symbol is spades, and you've guessed it, there's 13 spades. 13 times 4, 52 cards in total. And 4 of the cards are aces, so let big A represent the aces. 1, 2, 3, 4 aces. Can have the ace of diamonds, ace of hearts, ace of spades, or ace of clubs. So based off this, imagine a card is selected at random. Find the probability that that card is a spade. What's the chance of picking a spade? Well, there's 13 spades to pick from, so that's going to be 13 out of 52. Which I suppose if you wanted to simplify down, you could say that's a quarter. Probability of a spade is a quarter. What's the probability, though, of picking a spade, given that I'm telling you that the card's definitely an ace? So interpret this as like, psst, listen up, before you just select all the spades, I'm telling you, just narrow it down to just the aces. So this is like a whisper wall. So whispering the secret, it's an ace. So if I narrow it down to just the aces, if I just look here, out of those 4 aces, what's the chance that it's a spade? Well, only 1 out of 4 aces is a spade. So the probability of selecting a spade, given that you have to pick an ace, or given that it must be an ace, is that 1 ace of spades out of the 4 aces in total. Next, how about a probability of it being a spade if I told you that actually the card is not an ace? So what if a card was not an ace? From those non-aces, what would be the probability of selecting a spade? So the non-aces are all these here. Now, if you want to count them up, it'd be 48. Now, it'd be easier and more common sense just to do 52, take away those 4 aces. So this green region here is 48 playing cards. So if you're thinking, as I'm colouring in like a child, how many of these cards I'm colouring in green are spades, you can hopefully see that there's 12 spades out of these 48 in green. So 12 out of 48 of these are spades, so the probability of randomly selecting a spade, given that it's not an ace, is 12 over 48. I'm also going to simplify this down, and you'll see that's a quarter. Part D. What's the probability of picking an ace? Well, as you can see here, there's 4 aces out of 52. If I simplify that down, that's the same as 1 out of 13. This one, what's the chance of picking an ace given that the card must be a diamond? So if I just get rid of my colouring in from before and think about these next ones. So given that the card's a diamond, what's the probability that it's an ace? So let's have a look at all these diamonds. There's 13 of them. How many of those diamonds are aces? Well, there's 1 out of 13. And finally, F, what's the probability of it being an ace if I tell you that actually the card is not a diamond? Well, if the card's not a diamond, then that's going to leave us with all these cards. I'm going to colour in now in purple. If it's not a diamond, I'm just excluding that very bottom row. I'm just looking at these top 39 cards. So out of these 39 cards, which I'm colouring in purple, how many of these are going to be aces? I actually can't be bothered finishing colouring that in, so there you go, I'm sorry. You can see here there must be 3 aces out of a total of the 39 non-diamonds. And again, if I simplify this down, 3 over 39 is 1/13. For part G, let's just consider our results for A to C and D to F. What can be deduced from your results to A, B and C? Well, if you just have a look here at the answers to A, B and C, the chance of picking a spade is 1/4. Chance of picking a spade if I'm telling you it's an ace, that's still 1/4. The chance of a card being a spade if I tell you a card is not an ace, again, is 1/4. So what this means, based on what we mentioned a few moments ago, is because this probability is the same as the probability for B, which is the same as C, that tells us that the probability of picking a spade is independent of the probability of selecting an ace. If we also have a look at for D to F, where we're talking about aces and diamonds, then you can see here that these all simplify down to a 13th. And in the same way, because we're talking about probability of an ace, or an ace given that it's a diamond or given that it's not a diamond, it's still 1/13, whether it's a diamond or not. That tells us that the probability of it being an ace is completely independent of if the card is a diamond or not, and the other way around too. So to cut it short, for G, what this tells us is the probability of selecting a spade and the probability of selecting an ace are independent of each other. And to keep it simpler, likewise is the case for diamonds and aces for D to F. Let's have a look now at worked example 2. Worked example 2 is a school which has 75 students in year 12. So of these students, 25 study only humanities subjects and 37 study only science subjects. 11 students study both science and humanities. So talking this through carefully, we can do this in a table, because part A asks us to do a 2A table. So H for humanities, H dashed for students that don't study humanities, then a total. Likewise for scientists and non-scientists, and then a total. So first of all, what did we get told? For 75 students in year 12. So that's a grand total, so we can populate that bottom right box with 75. Next thing we were told is 25 students studied humanities subjects. So only humanities subjects means these students studied humanities but did not study science. So that 25 relates to this box here. We're then told 37 people studied only science subjects. So that means science without doing any humanities. So that would be S and H dashed here. And finally, 11 students did both science and humanities. So that's where the S and H meet. So S and H meet at this one here. So that needs to be filled in with 11. From that, the rest of the table can be worked out. So we can do 11 plus 37 to get the total science students must be 48. Whoops, that's the wrong colour. That's better. 11 plus 25, that's 36. We can now work out a few different things. What I'm going to do here is work out the number of students that do not study science by doing 75 take away 48. So 75 take away 48, that's going to give us 27. So 27 goes there. This row here needs to add up to 27, therefore. I've got 25 already. This must be the missing 2. Then this column, 37 add 2 is 39. And as a double check, does 36 plus 39 give us 75? Yes, it does. We can now use this to answer part B. So B part 1, what's the probability of selecting a student that does not study science and, because of intersection, does not study humanities? So the students that don't study science are these people here, and the students that don't study humanities are these here. So where they intersect, where they overlap, literally you can see is 2. So that there is just 2 individuals. So there's 2 items in the intersection, but because you want a probability, that needs to be out of the total in the sample space. So because it's not conditional on anything else, we're talking about all the 75 students. So that's 2 over 75. The next one, we want the probability of selecting a student that's a scientist given that they study humanities. So what we can do here in the same way is just think about what bit of the sample space we're looking at. So because here we're told that this student is doing humanities, we're restricting what we're looking at purely to this region here, just the humanities section. So the ones that are doing science in this is just the 11 of the 36 we've been told it must be. So that's going to be 11 over 36. And for part 3, the probability of a student doing humanities given that the student does not study science. So if this student doesn't study science, we're looking purely at the students that do not study science. So we're looking at all these people here in the S-dashed row. We're not looking at anything else, just these. You can see that the total number of people is 27. This is going to be out of 27, no matter what. So out of 27, how many study a humanity? That's 25 out of 37. So that's how you can do these using a two-way table. If you're wondering, which I'm sure you are, well, could I use a Venn diagram? The answer's, depending on the question, yes. The same can be achieved with a Venn diagram. That's going to be next lesson's focus. If you want a sort of sneak peek in, this is how you could do a Venn diagram and solve a question in a similar way. So based on the information of the question, this would be a starting bit, 37, 11, and 25. If you added those up, they would come to 73, so then you need an extra 2 on the outside. So you can come to the same conclusions to these from using the Venn diagram or the table. So after doing this chapter, you'll know both approaches and therefore have more versatility and confidence in terms of how to tackle these probability questions that might be thrown at you for your examinations. Lastly, worked example 3. So this time we've got a 5-sided spinner, numbered 1, 2, 3, 4, 5, and a 6-sided normal dice, technically a die, numbered from 1 to 6. They're spun and rolled together, respectively. So you spin the spinner, roll the dice. The sum of the numbers the spinner and dice land on is then recorded, so they're added together. So first of all, for part A, we need to draw a sample space diagram showing the possible outcomes. So what we need is columns and rows in a table, where rows will be for either the spinner or dice, and the column will be for the other thing. So something like this is a good idea. So I've done spinners for the columns, 1, 2, 3, 4, 5, and the dice of the rows from 1 to 6. So what we're going to do here is add these numbers together to fill in these spaces. So the next thing is to get these values here. So 1 plus 1 is 2, 3 plus 3 is 6, 4 plus 2 is 6, and so on. So you should realise where these numbers come from, I'm hoping. So part B is where it gets slightly trickier, but not too tricky, given that the spinner lands on an odd number, it says. So find the probability that the sum of the numbers is exactly 7. That's a bit of a typo, which bugs me slightly. So that should say is. So what's the probability the sum of the numbers is exactly 7, given that the spinner lands on an odd number? So I'm really focusing in on this idea here that the spinner lands on an odd number. So that's like a little rumour you're told. So everything else, zone out, just focus on the odd numbers for the spinner only. So hone in on 1, 3 and 5. We're only looking now at those highlighted numbers in that yellow. So these others now are not in the sample space we're considering, so for all our intents and purposes, they may as well not be there. So which of these sum up to be exactly 7? Well, we've got a 7 here, a 7 there, and finally a 7 there. So the probability of the sum being exactly 7, given that it's an odd number on the spinner, is actually 3 out of the total. So that's going to be 3 over. So we've got 1, 2, 3, 4, 5, 6 times by 3 columns. So it's 3 over 18, which, if you wanted to simplify, is 1 over 6. Finally, part C, state one modelling assumption used in these calculations. So put simply, what have we assumed to be true about the dice and the spinner? Probably a few things. You could be pondering what colour dice you've used, but that'd be silly and pointless. The key thing here is you'd have to assume the spinner and the dice are fair. You'd have to assume that each outcome is equally likely, which is the same as saying the dice and the spinner's fair, or you could say the dice and spinner are unbiased. So a few ways of saying essentially the same thing. So something like this would be fine to get you the marks. So both dice and the spinner are fair, unbiased, and each outcome is equally likely. So that's what you need to say for part C. So now it's over to you to try some of these on your own. What I'm going to suggest you do is to get your books out, turn to 2B, page 15 in the Stats and Mechanics book year 2, and just try all of that exercise. Check how you're doing regularly, and if you're getting stuck, either let someone know who you can work well with, or let myself know. And if you're still stuck, please do leave me a message on the comments, or send me an email, whichever way you can. I'll be happy to help if I find the time, so if it's urgent, do say so. Thanks for listening again, and stay in touch for the next video. But until next time, take care, enjoy yourselves, and be safe. Goodbye for now.